Well, it's time to start. I will begin. Heavenly Father, we thank you for this day. I thank you for this semester that's about to start. The students, just pray you to bless our work this semester and that you be glorified in what we do, Lord. In your name I pray. Amen. So hope you guys had a good summer. You may or may not know I'm James Cook. I have office hours that have been posted basically 8:55 to 10:30 Monday, Wednesday, Thursday, and Friday. I've got also an hour on Tuesday from 10:05 to 11:05, and there's one Friday afternoon. Anyway, that's all posted online, so you can find it there. This is a course in complex analysis, of course, and I have posted the first 4 chapters of notes. We're following my notes primarily. As a backup, we have, and maybe your copy looks better, this. Mine's a little worn, but whoa, exciting. But this is a great book for extra problems and just for a baseline of information, pictures, graphs, and so forth. So I'll try to assign some problems from here as we go, but I'll try to create other ones myself. So that's my first order of business today after I'm done teaching, is to write your first homework. So I'm hoping to have that posted later today. It'll be due next Wednesday at the start of class. I call the homeworks missions, right? So mission 1 is due next Wednesday, and then there's one due about every week after that. We have 2 tests, a few quizzes, but that's about it. Any questions about the structure of the class before I get into the material? No? All right. So the way this is going to go is I'm going to teach traditional complex analysis about 70% of the time in here, all right? And about the other 30% of the time, I'm going to be showing you things that you probably wouldn't find in many textbooks, right? So this is an experiment. You're part of an experiment. If it goes badly, everyone gets an A, right? So, wait a minute. Define badly. So this is convenient for me at the end of the semester when I explain, why did you give 100% of the students A's? I'd be like, well, it went badly. I promised them at the start, so sorry. Man of my word. What can I tell you? My apology. For the many weekly announcements this semester, we have a university initiative that we have to send a weekly announcement. I promise that I will do my level best to not start discussion boards in here. I realize it's a fear, but for now, I will try to only send you announcements which actually are substantive, that actually have something to say, but that's debatable. All right, so complex numbers. Let's talk about them. Any questions about the course? I get started here. So the first 2 lectures, I would say, are traditional complex analysis. Basically, my goal today and Wednesday is to introduce you to the basic arithmetic of complex numbers and a few of the most important examples of the functions. And so let's just get started. Definition. C, all right, complex numbers. It's the set A plus IB such that A and B are real numbers, right? And I'm just being a little bit vague here, but by definition, we say that the real part of A plus IB is A, and the imaginary part of A plus IB is B, all right? So, and here's just a convention I should mention, just to get started. Convention, if I could spell convention. If we write Z equals to X plus IY, right, it is assumed that the real part of Z is X and the imaginary part of Z is Y, and these are both real numbers. So if you wanted to write an expression which involves 2 complex quantities, by my definition, I'd have to say something like, if I wanted to talk about an equation with 2 complex variables, like, I don't know, z squared plus iw equals to 7, then my convention is that I would have to tell you at the start, let z and w be complex variables. Because by default, when we write something like z equals x plus iy, we want to have in our mind that x and y are real numbers, right? And if we had to, every time we wrote z equals x plus iy, to write off to the side x and y are real numbers, it gets old, right? So you should thank me for this convention. By and large, it's used in every book written on complex variables without saying so, okay? If in doubt, say where things are from, right? Like, well, that seems very hypocritical in that you've just defined the complex numbers without really telling me what they are. Fair enough. More on that in a minute. But before I get to that, I just want to tell you central definitions. So how do we add complex numbers? If I have a plus ib, and I want to add to x plus iy, how do we add these? Right? And how do we multiply them? To add, we just add real parts, right? I mean, nothing surprising here. A plus x plus I times b plus y. Like, yeah. Yes. Now, multiplication is a little bit more exciting, right? Because this gives us ax minus by plus I times ay plus bx. So this right here is really a definition, right? In fact, these are both definitions, all right? That's how you add complex numbers. That's how you multiply complex numbers. Equivalently, I could just tell you I squared is equal to minus 1, and we proceed normally, right? Let's work that out. So if we take that perspective, we have a plus ib times c plus id. Ooh, I'm sorry, I was using x, right? X plus iy. So we've got a times x plus iy plus b times, oh, I'm sorry, plus ib. I'm already regretting writing this, x plus iy. It's too late, I'm too far in. Let's continue on. So assume it distributes, right? That's a normal property, distributing across addition, right? And then distributing across multiplication also, so we have ax plus aiy plus I times bx plus I squared times by, right? And we assume that, addition's associative, right? So, I mean, I haven't written parentheses in to tell you which one I did first. We just added them, right? Don't even ask me where to put parentheses in. We just don't put parentheses for addition, right? It's associative. And likewise for multiplication, I can factor the I out, right? So we're assuming it's commutative. So this I squared is minus 1. We get ax minus by plus I times ay plus bx, all right. Now, I didn't have to derive that. I'm just pointing out to you that my definition that I wrote over here is really just equivalent to saying I squared is minus 1 and proceed normally, right? So what are properties of complex arithmetic? These are all the usual properties, right? If I have z1, z2, and let's say w in the complex numbers, then you guys can tell me what is z1 plus z2 times w? And what is w time, what is z1, z2 equal to? Right? What other properties might we think about? I mean, first of all, we distribute, right? z1w plus z2w, and multiplication is commutative, right? So complex addition, multiplication satisfies the usual rules of arithmetic. The multiplication is commutative. 0, right? There's a 0, there's a 1, just like usual, right? Okay. But, certainly there were mathematicians who rejected these things because they weren't real, right? Well, in the same way, mathematicians used to reject negative numbers, right? Because I mean, give me a ruler with negative length, right? And that to them was an argument that negative numbers weren't real, right? In the sense of reality, right? So the term complex numbers and the term I being imaginary are somewhat unfortunate because they're really just as real in the sense of existence as anything else in math, right? Now that begs a question, which is you just wrote these symbols and you defined these rules, but what are complex numbers really, right? So there are three popular models, concrete models to describe what complex numbers are. I'll share them with you. Number one is the one we'll actually use by default, which I'll say is the Gauss's. Now people have argued that this was, somebody was saying this wasn't actually Gauss, but Gauss certainly was aware of this. So he just said that C is equal to R2, right? Where what you do is A times B times, x comma y, what's it equal to? By definition, it's equal to AX minus BY, and then AY plus BX. So you can just think of, this is the definition, right? That's a multiplication of pairs of numbers in the complex plane, and you can work out that multiplication reproduces all of the properties that I just listed. In particular, if you look at the number 0, 1, right, times itself, what do you get with this definition, Gauss's definition? We have to follow it, right? We got A equals 0, B equals 1, X equals to 0, Y equals to 1, right? So you look over here, what happens following the definition? What's that? We get 0, yeah, we get 0 minus 1, right? And then what else? Yeah, 0 plus 0. So we get minus 1, 0. Now, let's see here. Well, that's okay, great. Notice also that if we take 1 comma 0 times xy, what's that give us? In this kind of weird way of multiplying vectors in the plane. What'd you get? What'd you say, Susanna? What'd you get? X, and then what? And y, right? So in other words, the vector 1, 0, when multiplied by any other vector in the plane, gives you back that same vector, right? That means that this pair is behaving like the number 1, right? And so you can identify that if you call this thing 1, quote unquote, right? Then what is this up here? It's minus 1, right? Now, you say, well, that's confusing. You're using 1 in 2 different ways. Yes, that's true. That's true. You got me. So if you want it to be more pedantic here and make them look different, you could say, well, this isn't 1. It's 1 plus I times 0. Do you feel better about that? And over here, this isn't just minus 1. It's minus 1 plus I times 0. See, now you can tell they're different objects. But anyway, my point to you is that Gauss's construction, right, allows us to reproduce this element, this weird element that's square is minus 1, right? And so this gives us a way of constructing complex numbers simply as pairs of vectors in the plane, right? So that's one model, right? This has been known since, I don't know, early 19th century, right? It's probably known to Euler in the mid 18th century, honestly. The second model, all right, is matrices of the form A minus B, B, A, right? If you take two such matrices and you multiply them, what else is going to happen? What do you think is going to happen? You're like, I had your linear algebra. I've already done this homework problem. Stop telling me reruns. I know, it's true. You got me. but not all of you have had my linear algebra, so let's see here. Ba-da-ba-da-ba-da. So if you look at it, these 2 by 2 matrices also reproduce this pattern, right? That if we have, I mean, we can think of this as being quote unquote A plus IB, right? And we can think of this as being quote unquote X plus IY, right? If we think about that matrix being representing that complex number, what's, if that's the correspondence, what complex number does this 2 by 2 matrix represent? It represents that complex number, right? So these 2 by 2 matrices reproduce complex multiplication simply as matrix multiplication. So that's another way you could construct complex numbers, just as 2 by 2 matrices. And then the third way you could construct complex numbers that would be a popular viewpoint is you could say you take real polynomials and you quotient by the principal ideal generated by x squared plus 1. In other words, you could say complex numbers are equivalence classes of polynomials, where the polynomial x squared plus 1 is treated as the 0. You're like, that sounds like gibberish. Unless you've had Math 422, which is 40% of what we do in that class is dealing with this construction, all right? So that's the grown-up way, let's say, of constructing complex numbers in terms of a quotient of a polynomial ring. Obviously, that's not the right approach to take in here, right? Because you guys have not had 2 semesters of abstract algebra. But I feel like we should mention it, all right? Because it is probably the way you'd think of it if you knew those things. For us, the most concrete and sort of friendly way of doing it is just to say, you know what, this is the definition. If we need to get into the nuts and bolts of things, let's define complex numbers to be pairs of complex, pairs in the plane, real pairs in the plane, where the multiplication is defined like this, right? So that is really just what I've already said. If you understand that A plus IB, by our convention, A comma B, our convention is that A comma B is A plus IB, right? And so what that means is that the complex number 1 is actually the unit vector in the x direction, right? And the complex number I is the unit vector in the y direction, right? All right, so they do exist. There's 3 different ways you could build them. Let me move along here. See, we could spend, hours and hours and hours on their construction. It really wouldn't add more insight to complex analysis. See, once we have complex numbers, we use them, all right? It's somewhat immaterial how we're actually constructing them. The point is that there is this set, A plus IB. It has I squared equals minus 1, and arithmetic works like usual. That's the takeaway message from what I'm saying here. I'm, of course, happy to talk to you more about existence in office hours or something if you want to. And we'll see these matrices again as part of a larger discussion. Next up, though, complex conjugation. Complex conjugation, really important idea. And here it is. So if z equals to x plus iy, then z conjugate, which we write z bar, is equal to x minus iy. So the complex conjugate says you just put a minus on the I, essentially, right? Now, maybe it's time to make a picture. So this is the real axis. This is the imaginary axis, right? So if I take a point here, z, right, which is x plus iy, where is the conjugate? It's down here, right? The same x, but minus y. So complex conjugation geometrically corresponds to like reflecting over the real axis, right? Like this. What are the properties of complex conjugation? So if we have z1 plus z2, and we take the complex conjugate of that, guess what? It's the complex conjugate of z1 plus the complex conjugate of z2. So complex conjugation is it's linear. It has this additive property. But much more surprisingly, it also has a multiplicative property. So the complex conjugate of z times w is the complex conjugate of z times the complex conjugate of w. That is a little bit more surprising. So let's look at, let me give these numbers, 1, 2. And so, you know, for me, this summer is a summer of unfinished business, all right? So my default way of writing mathematics is a little bit different than the first chapter is written. The first chapter is written sort of in paragraph form. I don't have a lot of propositions with numbers that are sitting by their lonesome, you know, with numbered lists of facts like I like to, all right? So the style of chapter 1 is not optimal for me, but it has the information that you need in it, all right? I'm just saying what I'm doing in class is kind of more like, you know, if I had another summer worth of summer to work with, might have done. So anyway, I know you're fascinated by this. Let me go on. So how to prove number 2? Because that would make an excellent test question, right? Prove this. How would you prove that? You let z equal to x plus iy and w equal to a plus ib, right? Then what is z times w equal to? We just, you know, defined this, right? It doesn't matter which order the letters go in, right? These are real multiplications. They all commute. Anyway, that is z times w, right? So what does that tell you the conjugate of zw is? Right? So the complex conjugate of the product of z and w is that. Let me call that number 1. But z conjugate w conjugate is x plus x minus iy times a minus ib, which is what? ax minus by plus I times, oh, not plus, but minus, because I got minuses, right? Minus I times bx plus ay, right? Which is equal to zw conjugate by 1, right? So what does it show us? It shows us that the product of the complex conjugates is the conjugate of the product. This is the multiplicative property of complex conjugation, all right? Very nice. Very nice property. Observation. If z is equal to x plus iy, right, then zz bar is equal to what? Yeah, we get x squared plus y squared. What is x squared plus y squared? I mean, going back to my picture, if this is z is equal to x plus iy, by the usual Pythagorean theorem, this is x, right? This is y. So that's the distance squared of z from the origin, right? So thus, definition. The length of z is the square root of zz bar. So this is either the length, absolute value, or modulus, depending on who you talk to. Right. So proposition. What's the length of the product of two numbers? In fact, it is the product of the lengths of those numbers. That is almost a corollary to what I have on the board. Let me go through the proof for you. So if we look at the length of ZW squared, that would be what? ZW conjugate, ZW times ZW conjugate, right? I mean, if you want, I can put in the square root and the square. There, you happy? The point is, all right. And then what is the, so this is what? This is ZW, Z bar, W bar, right? By the part 2 of my earlier properties, right? But then complex numbers, multiplication is commutative, right? So I can regroup the terms, and what does this give me? ZZ bar, right? WW bar, which is what? Length of Z squared, length of W squared. So then if you just take the square root of what I just wrote down, that gives us this property, that the length of a product of complex numbers is the product of their lengths. This is special, very special to complex numbers, all right? This is not the sort of thing that is true for other number systems, like I'll hopefully start to show you Friday. All right. So some basic inequalities that we might notice here. And in mathematics, we don't try to get rid of inequalities, we embrace them, right? So, like, that's an inequality, we need to get rid of that. Like, no, we need to write it down and use it, right? I tried, all right, fine. Whatever. Be that way, see if I care. All right, so of course, is x is less than or equal to the length of z. Y is less than or equal to the length of z, right? If x is negative, this is just stupidly true, right? Because a negative number is less than absolute value. And if x is positive, that is either the x, that's like one component of a two-dimensional vector. Of course, the length of one component of a two-dimensional vector is smaller than the length of the whole vector, right? So geometrically, these inequalities are pretty obvious. So use a little modern lingo for you. There you go. All right. Next up, reciprocals. So, in other words, we want to ask the question, does a complex number have a multiplicative inverse, right? So, we would like for z times z inverse, right? That should be equal to 1, whatever this z inverse is. So here's a game you can play. So my claim And you could derive this, right? But here's just a sneaky trick. 1 over z, we're just going to say, well, let me write it this way. We're going to say z inverse, rather, is equal to z bar over z bar. This makes sense to write down because z bar is a real number, right? So we're not assuming what we're trying to prove here by writing that down, because we know how to divide real numbers into complex numbers, right? We just divide both components. 1 over c times a plus ib, by definition, a over c plus I, b over c, if you wish, for c real. Okay, so, and then does this work? Well, if we try z times z inverse, what do we get? We get z times z bar over z bar, right? Which is equal to z bar times 1 over z bar, which is equal to 1, right? Because z bar is just the length squared of the complex number, so we know non-zero real numbers cancel and give us back the number 1. Now, maybe I'm cheating, all right? If this bothers you, you can go back to the Gauss viewpoint and derive it from the pairs, right? That'd probably be a good homework problem. Hey, I'm writing homework today. Well, this is a good conversation, although it feels more like a monologue with a little bit of snickering, which I'll take. All right, anyway, so yes, this is in fact the formula, our go-to formula for the multiplicative inverse of a complex number. Let me just write it down more formally for you. Definition. Well, this isn't really a definition, it's a result, but let's say technique. How do you calculate 1 over a plus ib? What you do is you write down a minus ib over a squared plus b squared. That's how to find the multiplicative inverse of a complex number. Lest I be accused of putting no numbers on the board today, let me try that out for some real honest-to-goodness numbers. 1 over 2 plus 3i, example, is 2 minus 3i over 2 squared plus 3 squared, right? So that's equal to 2/13 minus 3 over 13 times I. So sometimes I'll ask you guys to put things in the Cartesian form. This is the so-called Cartesian form, right? Cartesian form means that you're writing in the form a plus ib. This is not Cartesian form to start with, right? All right. And you could try multiplying that out and see if you don't get back the number 1 when you multiply that, right? All right. So why do we care about complex numbers? Lots of reasons. I mean, the whole semester, at least 70% of it, is, maybe 80%, is about why we care. But, you know, just to throw you a bone, if P of z is an element of C of z, all right, so what's that mean, this C of z? This is notation for saying that P of z is equal to a naught plus a1z plus a2z squared plus an z to the n, all right, with an not 0. I'm going to assume an's not 0, okay, but that's not necessary. The point is C square brackets of z is the set of so-called complex polynomials, right? So one of the reasons complex numbers are interesting is that the fundamental theorem of algebra says what? It says that P of z, such a P of z, can be written as, I can factor an out, and then I can say z minus z1 to the m1 times z minus z2 to the m2, z minus z, I don't know, let's say k to the mk. All right. Fundamental theorem of algebra says that a complex polynomial can be factored into a product of linear factors possibly repeated. This is equivalent to saying every complex polynomial of order n has n zeros, or n roots, possibly complex, possibly repeated. That's the fundamental theorem of algebra. It's one of the things that Gauss was obsessed with, right? It's no accident that he spent a lot of time thinking about complex numbers, right? This is not true for real polynomials, right? Not every real polynomial can be factored in this way. Can you tell me one that can't be factored in this way? What's a real polynomial that doesn't factor into linear factors? X squared plus 1, I like that. So this we cannot factor just using real values, right? How do you factor that? You enlarge your sphere of ideas, right? But you see, that is not a real factorization of that polynomial. That's a complex factorization. So complex numbers are algebraically complete in this sense, all right? Eventually, we'll prove this theorem, all right? But not today. All right, so this is all pretty basic stuff. I probably could have just told you to read it, and it wouldn't have been any worse for the wear, right? What I'm about to do is a little bit more calculationally intense, all right? But not that much worse. And that is the so-called polar representation of a complex number. So what is the polar representation of a complex number? Well, let me ask a slightly different question. What can you say about any two-dimensional vector? If I have a two-dimensional vector, right? Let's say A for a second, in the plane. We can write that as what? The product of a magnitude and a direction, right? Here, my notation would be A hat in physics, but in here we'd probably say the length of A times A hat, right? That would be my more, if I'm just talking about vectors in the plane, if I'm not in the context. But in complex analysis, right, we've got Z. And we usually think of it as a point. Of course, that point is identified with the vector, which gets out to that point. But you see, we can write Z as equal to the modulus of Z, right, times the direction vector. So you could call it Z hat. I mean, people don't usually do this, but it wouldn't be a wrong notation. Z is, after all, a vector. Putting a hat on something normalizes the vector, makes it a vector in direction length 1, right? But let's just be a little bit more, let's look at this a little bit more here. So here's my point Z, right? Here's theta, the counterclockwise measured standard angle, right, from the positive x-axis. And so Z is equal to x plus iy, sure, that's true. But right triangle trigonometry, right, supplemented by the idea of polar coordinates, the different signs, if you will, of cosine and sine, says that x can actually be written as what? It can be written as r cosine theta, right? And the y can be written as what? R sine theta, right? But of course, we have another name for this radius now, right? Radius is also the modulus, or the absolute value of the complex number. So you can factor that out. We have the modulus of Z times cosine of theta plus I sine theta. So cosine theta plus I sine theta describes the direction, the unit vector in the direction of Z, right? Assuming Z is non-zero, of course. I suppose if Z is equal to 0, then it's the 0. Okay, this description is not, it's a little bit degenerate there, right? What's the angle of the 0 vector? I mean, you can't be wrong, right? So this is so special, we have another notation for it. This is called e to the I theta. That's the definition of e to the I theta. E to the I theta, by definition, is cosine theta plus I sine theta, right? And so that's the polar representation of a number. Definition, Z equal to x plus iy is equal to the modulus of z times e to the I theta. So this is the Cartesian form. This is the polar form. All right. It's like, well, great. So what? Well, what are properties of the imaginary exponential? Right, so just to be clear, the definition is what I wrote in purple, right? So how about cosine and sine? Are they periodic functions? They are, right? If I take 2 pi times, let's say, j, right? Any 2 pi multiple, integer multiple of 2 pi, then I get back e to the I theta again, right? Because if we shift the arguments of sine and cosine by a 2 pi multiple, it goes back where it starts again, right? So it's immediately clear that we also have this 2 pi periodicity for the imaginary exponential. So some of you are wanting to teach algebra in high school, right? One of the things we drill into students about the exponential function in like college algebra, or I'm sorry, high school algebra. Which is it? Is it college or high school? We should make up our minds about that, you know? Just saying. Is the one-to-one property, right? The exponential's got the one-to-one property. We go on and on and on about this, right? This exponential does not have the one-to-one property. Far from it, right? You add any multiple of 2 pi times I to the argument here. Back where you started again. All right, so that's property. Another really, really beautiful property, which I will not prove today, but maybe I'll make a homework for you guys, is that e to the I theta times e to the I beta is e to the I theta plus beta. All right? So laws of exponents, at least partially, in the additive sense, they work out like usual, right? And there's also e to the I theta to the n power is equal to e to the I n theta. You also have that law of exponents. That number 3 is usually, it's got a name that is in fact de Moivre's theorem, which I'm mispronouncing. But if you look in the notes, I explicitly work out what that means for like n equals to 2 or 3. That's actually a really powerful trigonometric identity, pair of them, right? So these are properties of the imaginary exponential. You're like, well, okay, lovely. What are we going to do with it? Well, we're going to do things like solve the following problem. Oh, I forgot to say something. Let me just slow my roll here for a second and tell you something. All right. So I should probably just do an example. If I have z equals to 1 plus I, that's a nice one. Let's look over here. W equals to minus 2 minus 2I. All right, I'll just pick on these just to give us an example here, right? So I want to find, I've given them to you in their Cartesian form. We want to find the polar form, right? So I've made these easy enough that you can just kind of see that that's pi over 4, right? So the polar representation of this would be the length of z. What's the length of z? Right, square root of 2, and then e to the I pi over 4. So there you go, that's the polar representation. This one down here, what's the standard angle there? So this one we could write, let's see, what's the length of this? Square root of 4 plus 4, square root of 8, right? E to the what? E to the I. If we go like this, right? What is that angle? I believe that's 3 pi over 4, right? Yeah, this is why we can't have nice things. Let's see here. I didn't bring the juice either, so it's a good thing I made this error at the end. 5 pi over 4, thank you. Now, the 3, what was I thinking about 3? It's because another way you could go here, right, would be this way. And going that way, we'd have square root of 8 e to the minus 3 pi I times 3. Goodness gracious. 3 pi over 4. And I'm trying to put the, you can put the I before or after. It's got to go somewhere, though. All right? Don't poke your eye out. So these are, wait a minute, you mean to tell me that the polar representation of a complex number is not unique? Indeed, I do. All right? So the argument of W, all right, is equal to, well, theta, such that W is equal to the modulus of W e to the I theta. In other words, the argument of W is the set of all possible standard angles for W. This is kind of a drag, right? I mean, it's a set of values. But this is the geometric ambiguity of polar coordinates, right? We have to face it. What if you want to make a specific choice? Well, arg, as in arg of W is equal to minus 3 pi over 4, right? So definition. Arg of Z is equal to theta in little arg of Z such that minus pi not included less than arg Z, oh, stink. Don't want to write an inequality for a set. That's kind of awkward. Theta, less than or equal to pi. This is also known as the principal argument. All right. So the principal argument is the angle between minus pi and pi not minus pi not included, pi included. We want to have our pi. We just don't want to also have minus pi, right? You have your pi, but you don't also eat your minus pi, right? It's a common saying. No? But my theory is by saying this, we're going to remember that pi is in the principal argument, because one of my principal weaknesses is forgetting which one of these is in the principal argument. So I'm going to say we're going to have our pi, and we'll remember this is included, but that is not, right? So with that definition, any non-zero complex number has a unique and well-defined principal argument. So like up here, arg Z is what? It's in fact pi over 4 plus 2 pi k, such that k is an integer, right? That's some trigonometry for you right there. Well, I'm using that 2 pi periodicity to write that down, right? The principal argument of Z up there is what? It's just pi over 4. This language is important. We're going to use this language a lot, all right? So next time, what I'm going to do is I'm going to show you how we can use this polar representation to solve this equation, z to the n equals to w. And we're going to see is that this z to the n equals to w has n solutions that are given by what are called the principal nth, they're described by the principal nth roots of unity, and it's a relatively simple matter to derive the solution using the polar representation. All right. Once we've done that, I'm going to introduce you to some basic functions like the square function, the square root function, sine, cosine, some other things next time. So thanks, guys.